dx equal to 1 by 2x du. So from here we have the square of the antiderivative of x by the square root u. Yeah? The square root u dx is what? Dx is 1 by 2x du. So here is 1 by 2x du. X cancel, yeah? Half, who is lose the integral sign. So here actually is half the antiderivative of 1 by the square root u du. So 1 by square root u actually is what? Is u minus half power, yeah? So here actually is half u minus half power du, yeah? U minus half power du. So the antiderivative of u minus half power is what? Is half u minus half power plus 1 by minus half power plus 1 plus a constant c, yeah? So minus half plus 1 is what? Half. So here is half. Here is also half power. So half cancel, yeah? So the result is u half power plus a constant c. U is what? U is 1 plus x squared, yeah? So the result is 1 plus x squared half plus a constant c, yeah? So here means this antiderivative is here. So here we have minus. So the result actually is ln 1 plus y equal to minus 1 plus x squared half power plus a constant c, okay? So this is the result. This is the result, okay? Ln absolute value of 1 plus y equal to minus 1 plus x squared half power plus a constant c, okay? So this is number 3. So number 4. So for number 4. Number 4 is 1 plus x to the 4th power. 1 plus x to the 4th power dy dx equal to x cubed by y. Okay, x cubed by y. 1 plus x to the 4th power dy dx equal to x cubed by y. So here, the first step, the same, okay? We times dx on both sides. So here we times dx on both sides. So here is 1 plus x to the 4th power dy equal to what? Equal to x cubed by y dx. Yeah? So now we can see the left hand side we have x. So we should divide it 1 plus x to the 4th power on both sides. We divided 1 plus x to the 4th power on both sides. So here we have what? We have dy equal to x cubed. Here is y 1 plus x to the 4th power. Here is dx. Yeah? Now we can see on the right hand side we have y here. We have y here, so we multiply y on both sides, okay? We times y on both sides. So here we have y dy equal to what? Equal to x cubed 1 plus x to the 4th power dx. Yeah? So now we can see the left hand side we just have y, the right hand side we just have x. So we find the antiderivative. So we find the antiderivative y dy equal to the antiderivative of x cubed by 1 plus x to the 4th power dx. So now first here, the antiderivative of y half y squared, yeah? Half y squared equal to here x cubed by 1 plus x to the 4th power dx. So this antiderivative is what? We use the u substitution, that u equal to what? Let u equal to 1 plus x to the fourth power. Yeah, so u equal to 1 plus x to the fourth power. So du dx is what? Du dx is 4x cubed. Yeah, 4x cubed. So here we have du equal to 4x cubed dx, or dx equal to 1 by 4x cubed du. Yeah. So here this antiderivative actually is the antiderivative. Here is x cubed, 1 plus x to the fourth power is u. Dx is 1 by 4x cubed du. So x cubed cancel, okay? So 1 by 4 is a constant, moves through the integral sign. So here actually is 1 by 4. The antiderivative of 1 by u du, yeah? So the antiderivative of 1 by u, ln absolute mu u, yeah? Ln absolute mu u plus a constant c. So here for this u, we should replace by 1 plus x to the fourth power. So here is 1 by 4 ln absolute mu of 1 plus x to the fourth power plus a constant c. So the result is half y squared. Half y squared equal to 1 by 4 ln absolute mu 1 plus y, or 1 plus x to the fourth power plus the constant c. Okay. Of course, you can times 2 on both sides. Okay. So you can times 2 on both sides. So the result is y squared equal to half ln absolute mu 1 plus x to the fourth power plus 2c. Okay. Of course, 2c you use a c is all okay. So this is the result. So now this is the end of 9.1. Okay. And we will now introduce 9.2. So now we go to the 9.3. Okay. So 9.3.
Last thing, 9.2 is very important.
What important? So I think that you can read it in your side. Okay. And and in the examination, final examination, I will test you the 9.2 just for you.
Especially.
Just for you. Okay.
Yes. Okay, last thing.
Now we see the page 429. Okay. 9.3, second order linear homogeneous differential equation. Okay. Second order. Okay. Second order linear equations. Method 3 is the second order. Second order linear homogeneous. Second order linear homogeneous differential equations. Okay, so here actually is for this form. Okay, so e plus px dy dx plus qxy equal to rx. So here for this equation, okay, for this differential equation, so the highest order actually is the second order, yeah? The second order derivative. So this is the second order linear differential equation, okay? Differential equation. So when for this kind, or if Rx equal to 0, okay? If the right hand side, this function, if this function is 0, okay? If this function is 0, so we call it the homogeneous. Homogeneous, okay? If Rx not equal to 0, okay? If Rx not equal to 0, we call it the inhomogeneous, okay? Inhomogeneous. 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 So here this is the and actually we just focus on the homogeneous case. Okay, so dy dx squared plus px dy dx plus qxy equal to 0. Okay, we just focus on this case. Okay, we just focus on the homogeneous case. Homogeneous case. So before we introduce the second order differential equations, we first introduce a definition, means the linear dependent, linear independent. Okay. So I think that you know the definition. Okay. You know the definition in the linear algebraic. Yeah. So here means the linear. For example, f is a function and g is also a function, and these two functions are linear dependent. Linear dependent. Okay. If f and g, f is a function, g is another function. If these two functions set are linear dependent, means that if one is a constant, plus or multiple, okay? One is a constant multiple another, okay? Multiple of the other. So here, so this means the linear dependent, okay? F and G are linear dependent, means that one is a constant multiple of the other. So here means f function, this function fx equal to a constant times gx, or gx equal to c times fx. So if we have two functions, the two functions have this relationship. If two functions have this relationship or this relationship, then we said f and g are linear dependent. Okay, are linear dependent. So for example, for fx equal to sin x, and gx equal to 3 sin x. So now we can see these two functions. Fx is sin x, gx is 3 sin x. So we can see gx actually is 3 times fx. Yeah. So these two functions actually is the linear dependent. Okay, linear dependent. So and now, so of course we have another. So f and g, we have another linear independent. Okay. So here f and g are linear independent. Okay, linear independent. So this means what? So this means if neither, okay, if neither is a constant, if neither is a constant of, or if neither a constant multiple of the other. So here, if neither is a constant multiple of the other, okay. So in this case, we say that f and g are linear independent. For example, for example, fx is x, this function, okay? And gx equal to x squared. Now we can see these two functions. X equal to some constant times x squared. So you can see x can express x equal to c times x squared? No. Yeah. X squared equal to c times x? Of course no. Yeah. So here means fx, x and x squared are linear independent. Okay. Are linear independent. So for example, so this is the first. For the other, for example, fx equal to sin x, gx equal to cosine x. So now we can see these two functions, okay? So sin x equal to a constant times cosine x? No, yeah? And cosine x equal to a constant times sin x? No. So here also means sin x and gx are linear independent, okay? Are linear independent. So here now we have a result. We have a result for this equation. Okay, for this equation, the second order linear homogeneous equation. Okay. So now we have this result, okay? So consider the homogeneous equation, the second order derivative plus px dy dx plus qxy equal to 0, okay? So this is the homogeneous, okay? Homogeneous. While px and qx are continuous on some common open interval I, okay? So for this second order equation, then there exist linear independent solutions y1x and y2x on I. So this result tells us that for this equation, for this homogeneous equation, second order equations, when px and qx are continuous, then this equation has two linear independent solutions y1, y2, okay? So this result tells us there exists, okay? When P and Q are continuous, then this second order derivative or the second order definition equations has two linear independent solutions y1 and y2 on I. Furthermore, okay, giving any such pair of linear independent solutions y1x and y2x, a general solution on I is given by yx equal to c1 y1x plus c2 y2x, okay? So here means what? Here means just if you can find two linear independent solutions of this equation, then the general solution is in this form, okay? It's in this form. So this result actually is in page 429. 429, the system of 9.3.1, okay? Of course, I do not need you to know the proof, okay? But I just need you to know the result. For this equation, for this homogeneous, okay, homogeneous second order, for this second order linear homogeneous definition equation, we have two linear independent solutions y1, y2. Okay? And the general function is expressed by y equal to c1, y1 plus c2, y2. Okay? So now, so here this is the result. But now, we need to find, for this one, how to find the linear independent solution. How to find the linear independent solution. So here, now, so we focus on, okay, so now we focus on the easy case. For this case, so here, now we focus on here px and qx are function, yeah? So now if px and qx are constant, we focus on this case, okay? So here for this case, dy of the second order plus p dy dx plus qy equal to 0, okay, equal to 0. Here PQ are constants, okay? Are constants. So now we focus on this equation. Here P and Q are constants. So now we need to find the general solution of this function. I need to find the general solution of this equation, okay? Here PQ are constant. So now we need to find this equation, the linear dependent equation, linear independent solution of this equation, okay? So here. Now for this one, okay, for this one here, we find the solution in this form. we find the solution in this form. Y equal to E mx. Mx. Here m is a constant. We find the solution in this form. In this form. Okay. So now we can see for this equation, dy dx equal to what? For this function, e to the power mx. So dy dx equal to what? Equal to m e mx. Yeah. And so the second order derivative. So the second order derivative equal to what? So the derivative of this function, yeah, is m squared e mx. Yeah. So now we replace. So here we dy. So here we have dy of the second order derivative plus p dy dx and plus qy equal to what? So the second order derivative actually is m squared e mx. So the second here is m squared e mx plus here is p times dy dx. dy dx is m e mx. Is m e mx. The second, okay. qy is e mx. So plus q e mx. So now we can see this equal to what? We take out the e mx. We take out the e mx. Here is what? Here is m squared plus pm, yeah, plus q. This should be equal to 0, yeah? So this equal to 0, so now we can see this factor. A number times another number equal to 0. And this number, e mx, will not be 0, yeah? So here we have that m squared plus pm plus q equal to 0, yeah? So here we have what? So here we have m squared plus pm plus q equal to 0, yeah? Yeah? So here means what? Here means if m satisfies this equation, then EMX is a solution of this equation. So I repeat, okay? So from here we can see if m is a solution of this equation, then EMX is a solution of this definition equation. Yeah? Can you understand? So from here we can see we need to do what? We wanted to find the solution of this equation. Yeah. So we find the solution of this equation. So we find the solution in this form, exponential function. We find the solution in exponential function. Okay. So EMX. So now we for y equal to EMX. So this equal to here. Yeah. And we take EMX. This equal to 0. This equal to 0 because the first factor not equal to 0. So just this equal to 0. So here means when m squared plus pm plus q equal to 0, then if this equal to 0, so here means this will equal to 0, yeah? If m squared plus pm plus q equal to 0, then we have EMX m squared plus pm plus q will equal to 0, yeah? This equal to what? This equal to the left hand side, yeah? So here means if m satisfy this equation, so then this will equal to 0. Will equal to 0, so here means y equal to EMX is a solution of this function, of this definition equation, okay? So here, I repeat it, okay? If m satisfies this equation, if M satisfies this equation, then EMX is a solution of this differential equation. So this is the process. Okay, this is the process. Because you can see if M is a solution or if M satisfies this equation, so then here means this will equal to 0. So here means this will equal to 0. This equal to 0. So here means EMX is a solution of this equation. So so here we have so this equation. Okay, so this equation. What's the relationship between this equation and this equation? These two. Okay, these two equations. Actually, we have a name in mathematics. So we have a name. So here, dy dx squared plus p dy dx plus q equal to 0. Here p, q are constants, okay? Are constants. Here p, q are constants. So here, now we can see this equation is m squared plus pm plus q equal to 0. Here is m squared plus pm plus q equal to 0. So this equation and this equation we have a name. Okay, so this equation is called the oscillatory equation. Okay, oscillatory equation of this definitional equation. Okay, So here, the m squared plus pm plus q equal to 0. This equation is called the oscillatory. Okay, oscillatory equation of this equation. Okay. So here now we can see just how to find the oscillatory equation. Actually, you just need to replace the second order derivative by m squared and I'm sorry, here is q1. This is q1. Okay. Here's q1. So first, okay, you just need to replace the second order derivative by m squared, replace the first order derivative by m, and replace y by m to the 0 power. So here, replace the second order derivative by m squared, replace the first order derivative by m to the 1th power, replace y by m to the 0 power. So here we can open this equation. This equation is called the oscillatory equation. Okay, oscillatory equation. So here for this equation, okay. For this equation, actually, we have three cases. The first case is m squared plus pm plus q equal to 0. Actually, we have three cases. Okay. The first case is this equation. We have distinct real roots. Okay, distinct real roots. The first case, okay. The first case is for this equation we have distinct real roots. Real roots actually is what? For this case, actually, the delta equal to p squared minus 4q. If p squared minus 4q less greater than 0, if the delta equal to p squared minus 4q greater than 0, then we have two distinct real roots. Yeah. The first real root is what? The first real root actually is m1. M1 is 2 minus p plus the square root p squared minus 4q. Yeah? This is the first root. The second root is m2 equal to minus p minus the square root p squared minus 4q. Yeah? By 2. Yeah? So this is m1, this is m2.
So why you get delta equal to p square minus 4q equals 0?
Yeah?
Yeah, this is
So here is just for this case. Ax squared plus bx plus c equal to 0. Equal to 0. So here, when delta actually is b squared minus 4ac, if this is greater than 0, then we have two distinct roots. Yeah? Two distinct real roots. If this delta equal to 0, so this is the first one, okay, first case. So for this case, okay, so for this case, if we have two distinct real roots, so here means that the first solution is y1x actually is e m1x. This is the first root, okay, the first solution. The second solution is y2x is e minus 2x minus 2x. Or em2x, okay, em2x. So this is the two linear independent solution for this case, okay, for this case. So for this case, so the general solution actually is y is c1 e minus m1x e m1x plus c2 e m2x okay. So this is for this case, so this is the general solution, okay? General solution. So now for this case, I give you an example. So for this example, y plus minus y plus minus 6y equal to 0. So for this one, okay, for this one we need to find the general solution. So here y plus, so first we need to find the auxiliary equation, okay. So the auxiliary equation actually is reset. We replace y plus by m square. Yeah, m square we replace y plus first order by m, so minus m, and we replace y by m to the 0 power, so it's 1. So m square minus m minus 0 equal to 0. M squared minus m minus 6 equal to 0. So m is what? So from here we can see actually it's m minus 2, m minus 3. So here it should be m plus 2 times m minus 3 equal to 0. Yeah? So here, so from here we can see m1 is what? m1 is minus 2, m2 is what? Is 3. Yeah? M1 is minus 2, M2 is 3. So the first solution is y1x actually is E M1x. E M1x actually is what? It's E minus 2x. Yeah? So the second is y2x is E M2x. M2 is 3. So E 3x R. So the general solution, okay, so the general solution is yx equal to c1 times y1, so E minus 2x R plus c2 E 3x, okay? So this is the general solution, okay? So now, so I think that you can do, for this function, you can substitute the two here. So you can see the solution of this equation. So I think it's easy, okay? Because you can see E minus 2 plus minus E minus 2x plus minus 6 E minus 2x. Now we need to see the equal to 0 or not. So here equal to what? Plus is what? First problem is minus 2. Second problem is minus 2. So minus 2 times minus 2, yeah? So it's 4E minus 2x. Minus here, first problem, so here is minus 2, yeah? So here minus 2, so plus 2E minus 2x. Minus 6E minus 2x. So we can see 4 plus 2 minus 6. So actually 0, yeah? Of course, for the second you can do it like this, okay? So for the first case, if this auxiliary equation have two distinct real roots, the first solution is EM1x, the second is EM2x. So the general solution is C1 EM1x plus C2 EM2x, okay? So this is the first case. Now we do not have enough time to introduce the second case and the third case. So the class is over. Thank you.